Alright guys, today we're talking about cross sections, using known cross sections. Now there's only a certain amount that you can do. You can do circular cross sections, you can do rectangular, you can do square, you can do triangle. And it's all really based on, do you know what the formula of that cross section is? So if I'm doing a semicircular cross section, well, the area of any semicircle is pi r squared over 2. So we've got to know what the formula is, and then we also have to know kind of conceptually what's happening here. So the cross sections whose base is bounded by these graphs. So in my picture, I've got my square root of x already drawn. 0 is just 0, and the 9's coming here at 9. So we can kind of tell that we're looking at this area here as my total area, right? Now, we want to do cross sections that are semicircular. Now this is kind of hard to visualize. What we want to think of is we've got circles coming out of the page. So we've got these like semicircles here coming out of the page. Now I'm not so sure if these if this website here still works. It used to be great. Like it would have these exact problems and it would show you exactly what they were. So you might want to just go online and search around volumes of known cross sections. You probably want to put in the word applet, A-P-P-L-E-T, because they'll end up showing you a visual of what it looks like. Now, if you can't visualize it, or if you have no clue what the visual is, it doesn't really matter. You know what the volume, or you know what your area of each individual one is. We make it a volume, we're just going to put a little dx on the end, whatever width each of them is. Now the tricky part for this is if I was to blow up each of those semicircles, this is my square root kind of coming across here. This is my y equals 0. The radius of this semicircle here is not the height of the function. That's the trickiest part. The height of the function, this is f of x, whatever it is, in this case the square root of x, that's our diameter of our circle. So for here, our radius is half of f of x. So we can take our pi over 2 out front, and we're going to get a bunch of little cross sections. So to add them all up to get the whole area, we're going to integrate this. And our r squared, we've got to make sure we're taking our f of x, which is our square root of x, and cut it in half, because our function is really our diameter. And we don't have diameter squared, we have radius squared. And our bounds are going to be whatever bounds we think they are. In this case it's 0, well here's 0, all the way over to x equals 9, from 0 to 9. So we got our formula, we can plug and chug. This one, it's kind of easy to do by hand. So 2 squared is 4. I can pull a 4 out front, so I got pi over 8. Still from 0 to 9 of just x dx. So this one ends up being really, really nice. So 1/2 x squared, so 1 pi over 16 x squared, plugging that in from 9 to 0. So we got 81 pi over 16. If you're going to use your calculator to do this problem, the 81 over 16, you want to hit math fraction on the whole problem. Leave the pi off entirely. Don't even put pi into the problem, and then just tack pi on at the end. The other thing is, don't make it a decimal times pi. That rounded decimal times pi is really awkward looking. So that's the main part here. Let's do one more.